All right, so I want to share with you today my experience working on the issue of security in cyber-physical system, give a little bit of historical perspective, what we have accomplished, and what I believe is the road ahead. First of all, cyber-physical systems, what they are, we don't have a real formalization yet, I think, of cyber-physical system. But loosely speaking, it is this intersection of control, communication, and computing into the physical world with the idea or with the goal of understanding it better and then controlling it, as we are engineers. And there is a real technology push, which started more than 15 years ago. The early attempts to designing CPS actually gave a lot of inspiration for the research that I did during my PhD and also continuing. So I would say that one of the early attempts, let's see if this works, of doing designing CPS was closing the loop around the wireless sensor networks. So this was a video which was shot in 2003, where we were part of this DARPA project called NEST, which actually was quite successful. And what we were doing, we were playing pursuit evasion games, and we were closing the loop around the sensor network. You see these nodes stuck in the ground. And so the idea was that the evader was trying to escape the pursuer, but it was being sensed by the sensor network, which then was transmitting the information to the pursuer, who then tried to catch it. So so we took our control theory that we had learned in 2021, 2022, and we applied to this. And when we implemented it, we found that it doesn't work. This we made work because the funding agency was there, so we engineered the problem to make the demo work, which is something that we've all done shamelessly a number of times. And the reason was that these radios were analog, 900 megahertz radios, and they worked really poorly. There was a lot of loss of information, and control theory was not equipped to deal with loss of information. So to what we did, then we got into, this was great inspiration for all the network control system work that we did with Shankar, Luca, Massimo, Kameshwar, and other people. So we came back equipped in 2007 at the final demo, where we had a newer version of sensors, which were much better. We had, I don't know, in this field there were, I think, 120 sensors. We worked tirelessly to organize this demo. It cost me a relationship, but it was well worth it, I would say. And this, I mean, in the interest of time, I won't go through the whole video, but actually we had an helicopter, we had 5 or 6 helicopters. And it worked. So the sensor network was able to target the evaders, who were people, and then the pursuers were actually simulated. But it worked so well that DARPA decided to make this project classified and continued, which still boggles me, this decision. Anyway, so this is real data, and it was shown really real time there, and the generals and DARPA people were really, really impressed. Okay, so that was with networked. I would love to go to the credits, but I don't have time. Oh, Phoebus, Songway, a whole bunch of people some of whom are here. So, and then the next step was, so everything is connected. We have wireless sensor networks, and we soon realized that the networking and the computing part of it was going to be off the shelf. And when you start networking things and using off-the-shelf components, then the next issue is security, right? As control people, we never worried much about security. We never thought that anybody would mess with our system. We all wanted the world to be a better place. Guess what? Not everybody shares this great vision. And today, there is strong evidence that the next wave of attacks will targets physical infrastructure. Stuxnet was a fantastic example to motivate my research. I'm sorry for the centrifuges, but there's casualties that have to be accepted. So, and I think it's a matter of national interest. So I think, I don't know, the economics of it are still not clear, but I know that Shankar is making headways also in this area, and that a public-private partnership is needed. Some of this infrastructure are really safety critical. Motivation, several, cyber warfare we have seen, but also gaining commercial advantage. You might think of a company starting a stealthy attack to decrease the productivity of a competitor, so that as to gain a competitive edge, or as 007 showed us in the last 50 years, there could be just the reason of ransom, like Spectre movies. So what's the difference? That's the first question people always ask, right? And so I think that the issue, as Sarab also said, the issue of security here is really an issue of resilience. So we don't necessarily need to protect at all costs the availability, secrecy, integrity of information. But if we have an infrastructure, we want this infrastructure to keep operating, right, and to operate safely. And so, the physical system have inertia. So you cannot bring them to a halt immediately, right? Like what you do with your computer when you realize a virus, and you just shut it off and then you deal with it. You have to continue operating, perhaps under what we call graceful degradation. So which services do you preserve? Which ones can you do without? And the other thing is that patches in the physical world might be expensive. Think about the Chrysler, the Fiat Chrysler vehicle, which was hacked, right? What you need to do is you have to issue a recall, and that's millions and millions and millions of dollars. Okay, so on the other hand, there's good opportunities. Physical systems have fairly accurate models, and you can use and exploit the predictive power of these models to understand what goes on and develop tools that come from a system-theoretic world that we can use for the detection and resilience of physical infrastructure. And these tools are complementary to the ones that are offered more from in the cyber security realm. And I think we have really chances also to prove security properties and develop a theoretical framework to do this, right? Which is something that's somehow lacking in the cyber security area, where you have this this dynamics where you discover a certain vulnerability and you find a solution, right? We want to be a little more systematic so that we don't always chase the attacker. So let me give you some evidence that actually control theory and system theory is crucial to in this battle. And if I go to somebody who's a cybersecurity expert and I tell him, I have a vehicle which is moving on a straight line, right? And two sensors are used to observe it and to control it, a position and a velocity sensor, okay? And I'll ask him, if you were to protect one of them, which one do you think is more crucial for the safety of the system? Right? I don't think that they would have a clue, and I think it's not an obvious question at the outset. For instance, if I asked you, if you already know the answer, perhaps don't answer. So if you were to protect one, which one would you protect? The position or the velocity sensor? Position. And velocity? Okay. So it turns out that if you corrupt the position sensor, you can show that you can move arbitrarily that vehicle on the x-axis, and so the solution goes into generating exciting some zero dynamics, right? So if you do that, you can show that actually you can move this is the perturbation in the position, and it can grow arbitrarily long without incurring detection, okay, by remaining stealthy. Right? And and you can show that you can do some reachability analysis using ellipsoidal calculus. You have a lower bound and upper bound. You see that the area keeps growing and goes to infinity. Right? If you instead compromise the velocity sensor, then you still induce a certain perturbation, but this is bounded because otherwise you will incur detection. Okay? So that's something that really requires knowledge of system theory to do. And even if you do, then there's work to be done. It's not clear at the outset, as here there was a split decision on what to use. Other example, Stuxnet. David Sanger, I think he wrote also a book, comes up with this article in 2011 and says that the biggest single factor in putting it was the most sophisticated cyber weapon ever deployed. So, and the worm had two major components. One was to send the centrifuges spinning out of control, and so exert control on the system. Right? And the other was write out the movies, saying he recorded what the normal operation, then played those readings back, so that the people in the control room would not notice anything, right? So and so we took this and we wrote a paper. And where it says that the paper analyzed the effect of replay attacks, so played these readings back. And if you look at the abstract, there's a staggering resemblance with David Sanger's article. So you might say that we copied it, with the small difference that our paper was in 2009, so 2 years before. And also in that paper there was a solution to do that, because if you run analysis, you can explain why they were not able to detect such an attack. If you build a chi-square detector, there's no residue basically, and so your detection rate is the same as false alarm rate. And then there was also a countermeasure, which was, instead of just designing for performance, this UK star would be the result of your LQG, for instance, add a perturbation signal, make it zero mean, so that you don't drift the system from its operating point, but put some variance in it. And if you do, then your observation, which would look like this without this perturbation, will have a kind of a watermark over it. And you should be able to extract it. And if you can extract it, then the sensors are telling you the right things. If you can't, then perhaps they're telling you the wrong things. And if you apply, you see that your detection rate actually increases as the energy of this perturbation increases. There's interesting engineering trade-offs here, because as you perturb the system, you lose performance, right? But you increase detection rate. So of course you don't get to 1, but it works like a charm. So this was the Tennessee Eastman plant, a chemical plant, and we applied 2 controllers. To the left is the controller just designed for performance, and to the right the one with this perturbation signal. As soon as a attack occurs, here you will never exceed the threshold, even though it's very low, and so a lot of false alarm rate. And instead there, you almost immediately detect the attack. So it's useful. And other problems which are very simple and known for 80 years or more, they become open once you put an attack model into system theory. For instance, let's say that you have a binary detection problem, right? In any book, you will find a solution. This is joint work with Joao, his former postdoc, Kyriakos, and my former student, Yilin. So I'll show you the robust version of it. We also have the game theoretic version of it. So you have some prior on what's happened, either 1 or -1, and then you have certain measurements. So you build your log likelihood function, and then you do detection. Now, if a number of sensors are telling you the wrong thing, they know the right answer, and they want to induce you to make the wrong decision. If you use just a naive-based detector, where naive now can be interpreted in 2 ways, then you will be induced to make the wrong decision. So the question is, how do you make it robust? How do you find the optimal detector which will minimize the probability of error in the face of having a subset of these sensors compromised? The problem is very hard. Actually, I have not solved it yet. So let me skip this. But there are some cute results. For instance, if the number of compromised sensors is at least half, the best thing that you should do is throw away all your measurements, right? And decide based on your prior. So it is a nice recipe, because to an attacker it says, I don't need to compromise everything. Half is sufficient. It's kind of reminiscent of error correction coding when this 2 n comes. So if instead we are on the more normal case, less than half, then the problem you can set up as an optimization problem, but it's over sets, and you have Hamming distance. In other words, it's a tough problem. So the heuristic detector says that what you should do, and I'll give you the example from TripAdvisor. You're looking for a hotel, and you're looking at reviews of hotels, and assume that a certain number of them are either done by competitors or by the hotel itself. What you should do, throw away the best M and the worst M reviews and based on the one in the middle. And you can prove that this is optimal as the ratio of good to bad goes to infinity. Okay, so I'm going to skip a few things. This is related actually to distributed control and vehicle networks. So let's say that you have a platoon and a communication infrastructure, and let's say that up to 3 vehicles can be compromised. You want to, what should I measure, and what should the communication infrastructure be so that I can guarantee to detect an attack from any 3 vehicles. So you can set up this. It's actually a observability problem at the end of the fair, and you can find we designed a methodology to actually design both the observers and the communication infrastructure as to minimize a certain cost. So that's so what to do next? I think what we're still missing is that some of these results are constrained to the particular model, to the particular detector that you're using. So we would like to have a concept that abstracts away and gives more general results. And also we want to connect with the cyber world. We need tools that can be used in both worlds. And I really think that a good first step is using this causal information flow analysis, which it is a concept that actually was born in the computer science. John Rushby and people were working on these things. And the idea is pretty simple. You have a system, which could be any system. That's why it's general. And you have 2 inputs. And there is information flow when you are capable of distinguishing between these 2 different inputs from the outputs, right? And so this is the basis for detection. And it really connects, because the system could be anything. It could be a computer program, for instance, right? And it could be a dynamical system. And so we latched on this work, which goes all the way to the 70s, from probabilistic version in the 90s. And it also connects to privacy, because confidentiality is actually the dual of it. It's the absence of information flow. And we were able to actually recover a bunch of results, which they looked completely different and isolated. Instead, they're part of the same framework. And these are the results. They're not all from us. So I'm going to close here. I'm going to say happy birthday. Actually, I'm not going to say happy birthday myself. But actually, there was somebody who wanted to say happy birthday.
Happy birthday, Shankar.